Hello, my name is Elizabeth Gordon. Today I will be reviewing the physics of electroporation in cancer treatment. I will begin with a general overview of electroporation. Electroporation occurs when an electric field is applied to a cell. This creates a pore to channel objects inside of the cell. This has been used for a variety of medical applications. For example, in skincare, it's used to increase the permeability of the skin barrier. In cancer treatment, it is used to increase the efficiency of drug delivery. I will use the physics concepts of electric fields, potential differences, and capacitance to examine how electroporation is used to increase the effectiveness of chemotherapy in cancer treatment. In order to begin the process of electroporation, an applied electric field is applied to the target cells. In the equation for the external electric field, the magnitude of the electric field is set equal to the voltage applied over the distance between the electrodes applied. The distance between these electrodes is typically under a centimeter. Different types of cancer demand different types of electroporation. Depending on the cancer type, the person being treated will either go through reversible electroporation, which is used to deliver chemotherapy drugs more effectively, or irreversible electroporation, which leads to the death of the tumor cells. The difference in these processes is shown on the right. One type of cancer for which irreversible electroporation is used is prostate cancer. In order to perform electroporation on these tumors, the threshold that leads to prostate tumor cell death must be known. Due to the relationship between the electric field and the potential being proportional, reaching this threshold also causes a very high transmembrane potential value. This leads to the permanent formation of pores due to the disruption in the lipid bilayer and cell death. This level varies between different cell types, ranging from 423 volts per centimeter for a porcine liver to 1,135 volts per centimeter for a human prostate. In the study that examines these materials, the researchers found that the threshold for irreversible electroporation in prostate tumors was 506 volts per centimeter, over twice as small as the human body cells in the prostate's threshold. This could suggest, in general, that tumors have a lower capacitance or resistance than human body cells. Next, I will examine how potential differences, particularly transmembrane potential, affects the cell membrane during electroporation. The transmembrane potential refers to the difference in potential between the inside and outside of the cell. The equation frequently used to accurately calculate the transmembrane potential is called Schwann's equation. In this equation, the transmembrane potential is set equal to 1.5 times the magnitude of the applied electric field, times the radius of the cell, and times the cosine of the angle between the center of the cell and where the electric field is applied. If the field is undisturbed and no field is applied, then this potential is very small, such as in the tens of millivolts. In order for electroporation to work and for pores to form, the membrane potential must drastically increase. Typically, the transmembrane potential during electroporation is somewhere between 250 millivolts and 1 volt, much higher than the resting potential. This vastly increased potential leads to the formation of pores due to the disruption of the lipid bilayer's stability. In electroporation, the lipid bilayer acts as a capacitor. This is due to multiple properties. For example, the lipid bilayer is naturally very thin. Additionally, due to its ambipathic properties, it can hold charges on both sides. This gives the lipid bilayer a naturally high capacitance. This capacitance means that the time needed in order to form pores on the cell increases, due to the relationship between the capacitance and the potential. In the cell, due to these ambipathic properties, we can set the lipid bilayer as a parallel plate capacitor during electroporation. In the equation for a parallel plate capacitor, the capacitance of the lipid bilayer is set equal to the area of the cell, multiplied by the permittivity constant, and then divided by the distance between the electrodes affecting the cell during electroporation. The process in which the pores form in the lipid bilayer is shown on the right. This is shown in the equation where potential is equal to the charge of the field over the capacitance. Due to this relationship between the transmembrane potential and the capacitance, the high capacitance of the lipid bilayer means that a large electric field is required in order to raise the transmembrane potential to the level needed to cause irreversible electroporation for cancer treatment. As more pores form in electroporation, the cell capacitance increases due to the pores facilitating transport of molecules and charges. There is a large relationship between the voltage potential of pore formation and the capacitance. The cell can be modeled as an RC circuit, with the lipid bilayer acting as the capacitor and the membrane acting as the resistor. Therefore, if you want to model how the voltage potential changes over time with respect to capacitance, you can model this through the RC circuit equation. The relationship between the capacitance and potential is used to regulate pore formation. As stated earlier, as the pores form, the capacitance of the cell increases. Due to the relationship between the potential and the capacitance being inverse, this increase in capacitance will eventually lead to the transmembrane potential dropping below the required threshold for pore formation. This will lead to no more cells being formed in the cell. I will now review how these concepts in electroporation lead to the increased effectiveness of cancer treatment. In cancer treatment, electroporation, or electrochemotherapy, is used to directly deliver chemotherapy drugs such as bleomycin into the cytosol. The electric fields are applied a short time after the chemotherapy drug is injected directly into the tumor. The fields applied during this particular study are at a very high intensity, 1300 volts per centimeter. This may be to promote the rate of cell death, as shown in our examination of potential differences. If the potential reaches a certain level due to the field, the pores both allow the delivery of the bleomycin into the cell and are unable to reseal, eventually leading to the death of the tumor. As shown, these concepts lead to a very high effectiveness rate of electrochemotherapy. I used the rate of complete response given in a different study to compare the effectiveness of electrochemotherapy to regular chemotherapy. Complete response means that there's no evidence of cancer cells after the treatment. The rate of complete response in tumors treated with electrochemotherapy is almost 7.5 times higher than that of the control group. This indicates that the pore formation due to electroporation greatly increases the effectiveness of cancer treatment. I will now summarize the process of electroporation in terms of applied concepts. First, an additional electric field is applied to the area that pore formation is desired. By doing this greatly increases the transmembrane potential of the cell. This large increase in transmembrane potential leads to the disruption of the lipid bilayer stability, leading to the formation of pores. The speed of the formation of these pores is determined by the capacitive properties of the lipid bilayer as an insulator. Finally, these are the sources used in this presentation. Thank you so much for your time. I hope you have a great day.